All the elements that are heavier than iron, like the gold and platinum in your jewelry, the barium used in green fireworks, and the lead used in your car batteries, they were all created by nuclear fusion reactions in a fraction of a second during a supernova explosion. Or are they? The story is almost correct, except for these elements are not really created by nuclear fusion reactions, and they're mostly not created in supernovae. When I first learned that this was a huge misconception that I had, I got so many questions. Like, why do we say that these elements heavier than iron are not created by nuclear fusion reactions? And if not by nuclear fusion, how are they created? And if not in supernovae, where are they created? And most importantly, how do we know about all this stuff? Oh my god, so many questions, and I had no answers to all of them until I met Margaret Burbidge. And then my mind was truly blown. So the goal of this video is not just to learn, but like always, to rediscover where and how exactly are these elements that make up your jewelry or fireworks, how are these elements heavier than iron actually created? So if you're ready for this, let's begin. Let's back up a little bit. We all know about the incredibly beautiful but also incomplete story about how the elements are made. It goes something like this. The hydrogen and the helium were made in the Big Bang, and all the other elements were manufactured in the stars. By the way, you keep asking me where I get my t-shirts. Well, I've started making my own, and now you can buy them as well, okay? Stars are powered by nuclear fusion reactions. You probably know this, right? Because when lighter nuclei fuse together, the heavier nuclei are more tightly bound. As a result, they release energy, and the stars use that energy to counteract against gravity. So if you could peek inside the core of a very massive star, you will actually find shells of heavier and heavier elements which are being forged by nuclear fusion reaction. But that is only until we get an iron core. It is one of the most tightly bound nucleus in the universe. So if you try to fuse iron together, it will not release energy. You require energy, and therefore fusion stops. And that's why you can only use nuclear fusion to produce elements up to iron. And now, because there's no longer fusion, there's no longer a power source, gravity wins, and the core starts shrinking. And because of the extreme pressure generated inside the core, the electrons actually fuse with protons to create a neutron star. This is one of the densest things in the universe, and now the collapsing shell bounces off against this neutron star, sending a shockwave, producing a supernova explosion. And the story usually ends with one last sentence, which says that all the other elements in the periodic table are created in a fraction of a second during this supernova explosion. And it's this last sentence that we really want to pick apart in this video. And to do that, we're going to talk to... Who is she, you ask? Oh, just a regular badass astronomer. I mean, she was incredibly influential in a field that was completely dominated by men during that time. Not only that, when she was awarded a prestigious astronomy award, which was exclusively reserved for women, she rejected it because gender discrimination. And most importantly, she co-authored one of the most influential, arguably the most important paper ever written in astronomy, the B²FH paper. So Margaret, why are elements heavier than iron cannot be created by nuclear fusion reactions? I mean, I understand that fusing these elements will not release energy. They will, they're endothermic reaction, they absorb energy, but we're talking about supernova explosion. There's so much plenty of energy over there. So surely this must be happening, right? And Margaret says, Mahesh, fusing such heavier elements require hundreds of billions of Kelvin to overcome the Coulomb's barrier. And I'm like, I get it, but supernova. And she's like, that's not the point. Do you have any idea how much energy photons would have at such temperature? And I'm like, no, but why are we talking about energy of the photons? And Margaret says, well, you can easily calculate that just by using Boltzmann's equation, right? Like Kb into T, where Kb is the Boltzmann constant and T is the absolute temperature in Kelvin. So temperature in Kelvin, okay? So if you just plug in the numbers, you would find that the average energy of the photons at such high temperatures of hundreds of billions of kelvins would be about 10 to 20 mega electron volt. And I'm like, okay, but why should I care about that? Because this is the binding energy of all the nuclei. In other words, a photon with this much energy can actually rip apart a nucleus. So Margaret, what you're saying is if you want to fuse heavy nuclei, the temperatures required are so high, hundreds of billions of Kelvin, that even if we do achieve that temperature, the photons over there would be so energetic, they would actually rip the nucleus apart. And Margaret is yeah, exactly. And that's why you cannot have nuclear fusion of heavier elements. This is called photo disintegration. And I'm like, oh my God, I never really thought about this. So Margaret, it looks like it's going to be hard for nature to start creating heavier than iron elements, isn't it? And Margaret says, actually, Mahesh, it's going to be super easy, barely an inconvenience. I'm like, how? Use neutrons. During a supernova, a lot of neutrons are created. Some of them come from the photodisintegration at such high temperatures we spoke about. Others can come because you have a neutron star at the core of a supernova, right? So when something bounces off of it, a lot of neutrons get splattered off. And so these heavy nuclei like iron, for example, can start capturing a lot of neutrons, and that's how it can start creating heavier and heavier elements. And I'm like, Margaret, wait a second. Capturing neutrons does not produce new, heavier elements. They just produce the new isotopes of the same elements, right? Well, Margaret reminds us that, Mahesh, true, but when you capture a lot of neutrons, like what happens in a supernovae, nuclei tends to get unstable. Too many neutrons make a nuclei unstable. Remember that? We've talked about that in detail, as to why that happens in a previous video, but just to summarize, just like electrons, protons and neutrons inside the nucleus also have energy levels, and they fill it kind of like the electrons do. And so if you have too many neutrons, look, the energy level of the entire nucleus becomes too high. And so what happens now is that some of these neutrons will get converted to protons so that the overall energy can be reduced and the whole thing becomes much more stable than before. This is called the beta decay. It's called so because in this conversion, beta particles like electrons are created and even neutrinos are created, which I haven't shown over here because that's besides the point, also because I got a little lazy animating that. But long story short, if you have too many neutrons, if you capture too many neutrons, well, it becomes unstable and some of those neutrons can be converted into protons, and that's how you can create newer and heavier elements. Okay, so Margaret, what you're saying is because fusing heavier elements directly is not possible because of the huge Coulomb's barrier we get, instead what happens is they capture a lot of neutrons and then convert some of the neutrons into protons via beta decay. I find that hilarious because that's kind of like nature giving the Coulomb's barrier the finger. All right, so we now have our correct story. All the elements that are heavier than iron, like the gold and the platinum in your jewelry, the barium used in the green fireworks, and the lead used in your car batteries, they were all created by neutron captures and then a beta decay in a supernova explosion. Or is it? So Mahesh, now we know that neutron capture is the key to creating heavier than iron elements, right? So if you have a lot of neutrons flying around, more chances of the capture, more efficient this process becomes. So supernovae definitely creates a lot of neutrons, and back then we thought that supernovae is the only source of creating neutrons. But where else do you find a lot of neutrons packed together? Neutron stars. The core of the neutron star is packed with neutrons, and the density is that of an atomic nucleus, one of the densest things in the universe besides black holes, depending on how you think about density, by the way. But there is a thin crust of heavy nuclei like iron and nickel over here as well, which can act like seeds to capture these neutrons. But wait a second. We need some kind of an explosion to set this in motion, isn't it? What kind of an explosion can do that? Well, what if you have two neutron stars orbiting each other? Then they can lose energy due to gravitational waves and crash into each other. And when that happens, of course, they create a black hole, but a lot of neutrons are whipped out, and you have a lot of neutron flux over here, a perfect site for an efficient neutron capture. So today we think that neutron star mergers, they are the dominant sites for creating such heavier than iron elements in an explosion. But wait a second. Neutron star mergers are way more rare compared to supernovae because you need two neutron stars orbiting each other, right? And yeah, they are, but we believe that the efficiency is so high that it compensates for that. But the big question is, do we have evidence for this? Well, certainly not during Margaret's time, because back then the concept of neutron stars was just being theorized. But today we do. You probably know that in 2017, humanity for the very first time detected gravitational waves from a neutron star merger. But what else happened is we looked at the signature, the optical signature that comes during the neutron star merger, and from that we were able to actually see, we were able to detect heavier than iron elements being formed. In fact, our estimates showed that roughly about 10 Earth worths of gold and platinum alone were formed during that one, neutron star merger that must have happened, I think millions of years ago. So yes, today we have proof that it is indeed the neutron star merger, which is the dominant site for creation of these heavier than iron elements, not supernovae, neutron star mergers. Okay, so putting it all together, we finally have our story. This means all the elements heavier than iron, like the gold and the platinum in your jewelry, the barium used in the green fireworks, and the lead used in your car batteries, they were all created by neutron captures and a subsequent beta decay, mostly in neutron star mergers. Or is it? Turns out that neutron star mergers and the small contribution that we get from supernovae, they're collectively responsible only for creating about 50% of the isotopes that are heavier than iron. So the big question is, what about the remaining 50%? Where do they come from? And again, how do we know about all of this stuff? Well, to answer that question, Margaret says, let's get into the details of the neutron capture that's happening during explosive events like this. So for example, during a neutron star merger, let's say we have an iron nucleus over here, okay? It is capturing lots and lots of neutrons per second very rapidly because there are so many neutrons over there, right? In fact, the iron has become extremely unstable right now and it wants to undergo beta decay. Maybe it even does, but it's capturing neutrons at such a staggering rate, it just keeps accumulating neutrons until it reaches a point where it can no longer just hold neutrons anymore. And only once it reaches this point, it'll stop capturing neutrons, and now it can beta decay and convert those neutrons into protons and eventually get to a stable element. And you can see now this new stable nucleus has a much higher atomic number compared to iron because there are so many more protons so many new protons compared to what we had before, right? This is what we call the R process, rapid neutron capture. R stands for rapid over here. This is what must be happening in explosive events like neutron star mergers and supernovae. And the beautiful thing about this is that we can even predict what the end elements of the R process would be, where it would naturally end up. If we do the math, which we're not going to do it, but if we do, it turns out that R processes should end in elements like gold and platinum and other elements like selenium, for example. So these must be the natural endpoints of the R process, theoretically. Now, if that is true, then if you look up in the sky, then these elements, which are the natural end products of our process, these elements must be abundant, right? Because they should get accumulated. And so we looked up in the sky, and guess what? That's exactly what we found. We found that elements like gold, platinum, and selenium, which are the natural end products of our process, they are indeed more abundant compared to their neighboring isotopes. And that was a huge evidence in support of our process, in support of neutron capture, which is insane if you think about it, right? But there was a problem. We also found some other elements to be abundant compared to their neighbors, which are not the end products of our process. For example, barium and lead. They, in fact, turns out that they get skipped over by the R process. So what's causing them to get accumulated was the big question. What's going on over here, Margaret? Margaret says to answer that question, she and her team came hypothesized that there must be another way neutron capture must be happening. One that's happening much more slowly so that it doesn't skip over any element. For example, let's again start with iron. And let's say you capture now 1 neutron per month. So you capture a neutron, you wait for a month. If it's stable, fine, it stays that way. Capture another one and wait for a month. If it wants to decay, it can decay. And now look, the next element can be formed. And then you wait for another month and see if you want to capture another neutron. Again, if it's stable, it's stable. And then if you want to decay, well, again, you can decay. So you can get the next element. And maybe now you'll get to the element like barium and lead. What's special about barium and lead is that they have a neutron magic number. So just like how in noble gases, electrons are completely filled and so they will not react with any element, and that's what makes them noble and stable. Turns out the same thing happens at a nuclear level as well. Certain isotopes of barium and lead, they have a neutron shells which are completely filled. And as a result, they will not accept any more neutrons after that. And so look, in this slow neutron capture process, barium and lead and elements like these, which have neutron magic numbers, they tend to be unnatural endpoints, right? And so if a process like this happens, then these elements can build up. So Margaret and her team hypothesized that there must be an S process as well. S stands for slow neutron capture, allowing enough time for beta decay to happen. But the big question now, the final question now is, where exactly does S process happen? I mean, clearly it cannot happen in explosive events like neutron star mergers or supernovae because that's where you get a rapid flux. Where do you get 1 neutron per month? Where does this happen, Margaret? Turns out that there are certain dying stars in which nuclear reactions can produce neutrons. And so that would be a perfect site for the S process. But wait, do you see how radical this claim is? I mean, so far we used to think that all the heavy elements were produced in an explosion. But now Margaret and her team are challenging that and saying, about 50% of those elements heavier than iron are produced in a dying star. Not explosion, but in a star. That is an extraordinary claim back then. And extraordinary claims need extraordinary evidences. So Margaret, what's the evidence for that? And Margaret asks Mahesh, what do you think? What would be the evidence for finding S process, that S process indeed happens in a star? And I'm like, oh, I know. Just point your telescopes at those particular stars and see if you can find spectral signatures of elements that are created by S process, like barium and lead. If you see them, then that's evidence that they're over there, that they're indeed present in the stars, and therefore they must be created over there, right? And Margaret says, not really. Just because you find the elements in a star doesn't necessarily mean they were created there, right? It's possible that those elements were created outside and they found their way into the star. Just like how all of the iron that is there in the earth right now were created outside of the earth and it's found its way into the earth, right? So just because you find it over there doesn't mean, it was created over there. I'm like, okay, fine, that doesn't work. So then what do we do? Look for radioactive isotopes that have a very short half-life. And I'm like, that is ingenious. I mean, if you detect a radioactive isotope, an isotope that only has element that only has radioactive isotopes with a short half-life, say for example radium, which has only a half-life of 1600 years, then if it was created outside, then there is a very good chance it would have decayed long before it has any time to enter into the star. So if you detect radium inside the star, you know for sure that it was created in the star. Amazing. So all we have to do is look for elements that have only radioactive isotopes and short half-lives. That means we have to look for elements above bismuth that have very short half-lives, right? Yeah, the problem though is that all the elements after bismuth can only be created in our process, because remember, S process ends in lead. So that doesn't work. Oh no. Okay, so this means we need element which only has radioactive isotopes, which are heavier than iron but lighter than lead and has a relatively short half-life. Do we have an element like that? Luckily we do. We have technetium. It doesn't have any stable isotopes, only radioactive isotopes. It is heavier than iron, lighter than lead, and the maximum half-life it has is about 4 million years, which is very short compared to the life cycles of these stars, which is hundreds of millions of years. So if we could detect technetium in stars, that would be a strong evidence of S process. So it all boils down to this, trying to detect technetium in stars. So what happened? Did we detect it? Yes, we did. In fact, an astronomer named Paul Merrill, just before his retirement, detected technetium in those particular stars. And since then, we have detected a lot of technetium stars. So the fact that we've seen technetium being found in stars is a proof beyond doubt that indeed those elements were created in the stars themselves, and therefore S process is indeed a thing that happens in these stars. This is how we know today that about 50% of these elements heavier than iron must be forged in those dying stars. Oh my God. Putting together all this reasoning and evidence and so much more, Margaret and her team wrote what some people call the most important paper in astronomy, the B-square FH paper. It completely revolutionized the way we think about stellar nucleosynthesis. So now we can put it all together, you and me, for one last time. You can say it with me. All the elements that are heavier than iron, like the gold and the platinum in your jewelry, the barium in your green fireworks, and the lead in your car batteries, the 50% of them are created by the R process in neutron star mergers, and some of them in supernovae as well. And the remaining 50% of them are created by this S process, the slow neutron capture process in certain dying stars. But I guess the broader message over here is that whatever we learn as facts about this universe are actually conclusions that scientists have made based on logic, reasoning, and evidence. And learning about them is so much more richer than just learning about the facts. And one of the cool and free ways to do that is by using Brilliant, who has sponsored this video. Why do I recommend Brilliant? Because just like in this video, Brilliant helps you rediscover concepts by reasoning and building intuition using a hands-on approach. But not just in physics or math, but also in data, programming, and even AI for that matter. For example, check out their course on how LLMs like ChatGPT works. It lets you interact with it to rediscover ideas of word probabilities, predictions, tokens, and so much more. And because they have bite-sized lessons, you can learn on the go and level up anytime you have a few minutes to spare. I've been asking my students to use Brilliant from way before they have started sponsoring me. So if you want to try everything that Brilliant has to offer for free for a full 30 days, then you can go to brilliant.org/FloatHeadPhysics. The link is in the description, or you can just scan the QR code, and you'll also get a 20% off on their annual premium subscription. Not only does it help you become a better problem solver, but you also help support my channel. Thank you, Brilliant, again for sponsoring the video, and thank you for watching. I hope you have a Merry Christmas and a Happy New Year.